Hello, I'm Ken Graham. I'm a general machinist here at the School of Engineering in the machine shop. I'm going to point out a few of the dangers and hazards that you'll want to keep in mind when operating a milling machine. Okay, number one, when you're in a machine shop, you're always going to have your safety glasses on, right? As soon as you walk through the door. Number two, make sure you don't have any long sleeves or are wearing gloves, okay? Roll your sleeve up. If you have long sleeves, roll it up to your elbow, okay? All our shop coats have been tailored to cut the arms off. The reason is, if a milling machine, if a cutter grabs hold of you, it will show you no mercy. Let's have a look and see what I mean. Okay, so here we are. We're on the milling machine and we're getting a nasty sharp chip. So we think we'll be smart and put on a glove. Now, we're gonna just flick off a chip. Let's just say a long stringy chip was on there. I'll just flick it off. Okay, so now, thank God for me, that wasn't my real hand, because it would be right out of my socket. Remember what I said? These machines have got a lot of torque. They may not have a lot of horsepower. This one has 3 horse, but when it goes through the primary and the secondary clutch, the torque is phenomenal. It would pull a bulldozer out of the mud. So if we take a look here, we can see what would happen. Okay, a lot of the cutting tools are sharp as a razor. When we talk about high-speed steel cutting tools, they cut by shear, so it cuts like a knife. They have to be sharp as a razor. Be careful how you handle these. Don't just grab them by the cutting edge and yank, or you'll end up with a dandy laceration, okay? The same thing goes when you're putting the cutter in the spindle and when you're taking it out. Grab the shank portion, the smooth section that doesn't have a cutting edge. Don't grab the primary edge where it's got a sharp cutter. So in the case here, I'm going to remove this cutter. Now I'm holding it, if we see where my finger is, that's the end of the sharp cutting edge. I'll hold it up here so that when I take it out, I won't be cut. And at the same time, be wary, if you were to drop that and that was to break free, this will just fall out. And when it hits the steel, it's probable that it would shatter a small portion. But that's okay, because you got your safety glasses on, right? If not, oh well, I told you so. Patches are cheap this time of year for the eye. Now, when I put it in, again, like I say, I'm going to hold the shank, not the cutting edge. Because when it draws up, it will lift it slightly. Okay, so we're gonna be wary of those sharp cutting edges, right? Another thing to be aware of when using a milling machine is it takes a moment for the inertia to stop. So in other words, I'm going to shut it off. 1 steamboat, 2 steamboat, 3 steamboat, 4 steamboat, 5 steamboat, 6 steamboat, 7 steamboat. Oh, is that a paddle wheel? Anyway, you get the idea. It takes a moment to stop. Remember what that simulated hand looked like, okay? Just wait for it to stop before you grab, start flicking around your part, clearing off chips. Be patient. Okay? Okay, another thing is, our milling machines have got power feeds for the table. So, we can have the table traversing as we cut when we're face milling or cutting a slot, a keyway perhaps. Now, the feed is independent of the spindle, so make sure that you shut the feed off prior to shutting the spindle off. Otherwise, your table will continue to traverse, and the cutter could be in such a position that it may plow into a shoulder further along the part. Perhaps you've had to use a clamp to hold your workpiece. It could plow into the clamp, or anything else like that, okay? So make sure you shut the feed off first. And here's one thing about these feeds, okay? They are deadly close, and I mean too close to the hand wheel, okay? So here's the hand wheel. Here's our lever for our feed rate. You can see how close that is. So if I bump the feed rate up, if I was to shut that off, you can see there's a good possibility that my hand could get drawn in by the knuckle on the handle. So be very careful. Sometimes it's wiser to slow it down and then do it, or carefully come in on the outside so that you're not drawn in. Okay? It's kind of a design that could have used a little more forethought. I guess we could take the handle off, but then we'd have to walk to that side all the time. So it's up to you, but be aware of that. Okay, on these machines, the large machines, there's 3 of them. And on all 3 of those machines, we have a power feed for our table. It's right here on the pendulum control. So we can bring the table up and down with power feed. I mean, it's not blistering fast, but it's moving quick enough. So if I'm focused on something on my table, I don't know what, but I'm focused on something here, I may not be paying attention to where my exterior is in relationship, say, to the handle here on the cross slide. Now, I wouldn't want to bring that down onto myself, or the power feed. Remember, it's going up and down with the table. So be aware of your surroundings whenever something is moving. Okay, when we cut on the milling machine, what we like to do is have enough cutting pressure on the material and the cutting tool to force those chips to break. Break into pieces that we can dispose of or clear easily. Okay? So if I look at these chips, now it's an assortment of plastic and steel and whatnot, but this is a good chip. They're small. This is a steel one. Okay? So that's a steel chip. An ideal steel chip using a carbide will be shaped like a figure 9 or a figure 6, depending upon which way you want to look at it. What that tells me is I've put enough cutting pressure to force that chip to break. So it's easy to get rid of off the machine, easy to get rid of off the floor, and easy to dispose of into the dumpster. Okay? And also, if I'm forcing it to break, it tells me I'm making the most of my cutting time. Okay? some aluminum ones. Sometimes the aluminum just a little bit bigger, but still it has kind of that shape. Short, bit of a radius, number 6 or number 9. So these are all good chips. Now, if you are feeding too slow, in other words, the cutter's just sitting there rubbing, we'll end up with a long stringy chip. Very hard to clean off the machine. Often it'll snag to the cutting tool. Hard to get off the floor, sticks to the broom, pain in the butt to stick in the dumpster. So this is not what we're after on a milling machine. And the steel chips are as sharp as a razor. So there, I just broke one off. Here's a long one here. The entire length is as sharp as a razor, okay? So if you have to remove chips like this because you fed too slow, don't grab them with your fingers. Either grab some pliers or grab a hook. We have several hooks that we've made, just a simple hook out of a thin diameter, like a 1/4 inch with a 90-degree bend. You can hook onto these and pull them free of the cutter. All right? Okay, so here's another thing to watch out for. All the machines have got an airline. Okay? We use these to clear chips from our part when we're taking them out of the vise, putting them in the vise, what have you. Maybe blowing chips off the table. Okay? When there's accumulation of chips and you're going to use your air nozzle, before you pull the trigger to clear those chips, look past where they're going to go and make sure that no one is standing there that are going to catch these chips in the face at high velocity. Okay? It's a good way to start a fight in a shop. Okay, another safety concern you want to keep in mind, the table of the milling machine makes a really convenient spot to put your wrench, some of your cutting tools you might be using. You know, it's right there, it's easy, your vernier. But remember, if it's got crap all over your working area, at some point it's going to go on the floor. Like, I need that wrench. Now, if that's my foot, well, that's my own fault. But if I've got a partner working on the side of the mill and he's trying to observe what's happening and I get him in the foot, that's not great. Okay, so bear that in mind. No clutter. It'll make your job easier and it'll make it safer. Okay, so another thing you want to look for is where you're going to be firing the chips. Okay? For example, if you're about to initiate a cut, you want to make sure that you're not firing the chips right into your face. At least I would hope. More often than not, you'll be working right to left because the cutter is turning clockwise. So if we just bring this up a little bit, we'll kind of take a look and see what I mean. Okay, so I'm ready to start my cut. I know which way the chips are going to go, but you may not. So test the water. Don't just put the power feed on if you're going to use the power feed, or don't go start cranking full throttle. Ease into it and just see which way the chips are going to go so you don't get them in your eye. Okay, I can see the chips are flying clear. So if I wanted to, I could utilize my power feed, and I wouldn't have to worry about getting them in my eyes. Now let's say I still wanted to do some milling. And I was going to come this way. Again, I would test the water. Flying right in my face, right? But if I didn't test the water and I had very little exposure in a machine shop, I might do something like this. Kind of going right in our eyes. So make sure you know where the chips are going to go. With a high-speed steel, you can see that they fly maybe 5 or 6 feet if you're using aluminum. But where the real danger comes from is if you're using a carbide cutter and your RPM is way up there, let's say 2200 RPM, the diameter of the cutter is 1.5 inches. So the surface feet on the outer diameter is tremendous. I can make the chips strike the other machine and have my floor clean. Okay, so you want to make sure. Another thing that you want to look for is make sure your floor is clean. In other words, if you come to the machine or if you're working on the machine and you're removing a lot of metal and covering the floor with chips, it can get really slippery, especially on the concrete. Not too bad on the rubber mat, more of an inconvenience, but on the concrete it can be very slippery. So if that's the case where you're just covering the floor, just take a moment, grab a broom, just push the chips to the base of the machine temporarily, and that'll clear a path. Now, if you're machining plastic, those chips are very slippery. So keep an eye on the floor if you're machining plastic. Okay? Another thing to look out for, all these machines have a non-captive lubricator system. So when we lubricate the slide at the start of the day, any excess oil just tends to drip off the end of the slides or the screws. And on these machines, this is where you'll see predominant oil. Right here. You can see that. There we've got some oil. Okay? So if you get to the machine and it's got a big oil spill or a collection of oil, just grab a rag, give it a wipe. Again, it's not too bad on the rubber mat. But the second you walk off that rubber mat onto the cement with oil on your shoes, it's time for a break dance. And hopefully not a broken bone. Okay? Alright, welcome back. We're looking at a 1.5-inch face mill. Face milling, a depth of cut 1/8 of an inch, and we're going to be using a feed rate of 16 inches per minute. So let's just get a close-up and see what's happening. Now that was a conservative cut. Really, I'm running quite slow compared to what the maximum speed and feed could be. So if I look at the chart and I decide that everything is perfect, my machine is rigid, my setup is rigid, then I'm going to bump it up towards the maximum. Let's say we're going to go 3,600. And this time, we're going to really hog it off. We're going to feed it at 36 inches per minute. So this would be similar if you had to remove a lot of material in a hurry. There we go. It's a thing of beauty. We're only making money when we make chips. Now, of course, when we utilize a quicker feed rate, our surface finish will become a little rough. So, as I said, I would use this in a roughing environment, just trying to remove some excess material. When I go to finish the surface, I will adjust the speed and feed accordingly. Now, let's have a look at these chips. Okay, so here's an assortment of the chips we just produced. You can see that they're short. We used enough cutting pressure to force the chip to break. That's what you need to do. You have to make the cutter work. If you apply too light a feed rate, you end up with a long, stringy chip. This tells me two things. You're not making any money for the machine shop and you're wasting time. Okay? You have to force the chip to break. It also makes for much easier chip disposal, as you can imagine. So this is a good chip. It's breaking. We can see the depth of cut. We're pushing it fast enough. We measure across that cross section. It will measure 1/8 of an inch. That's exactly what we removed. Okay? So now, what I'm going to do is, I had just mentioned before, I'll run the machine more towards the maximum recommended RPM, and I'm going to bump the feed rate up considerably. And I'm going to hog even more, just to show you it doesn't hurt to run a cutter too slow. Remember, you can always bump it up. But if you start too fast, you'll be replacing the inserts and or the cutter itself. A very expensive proposition, completely unnecessary. So make sure of your cutting speed before you start your cut. Okay, so here we go. We're running 4,500 and we got the machine going to its maximum feed rate, 39 inches per minute. Let's take a look. Ah, it's money to my ears. Okay, so you saw me took a very easy conservative feed, 16 inches per minute. Depth of 1/8 of an inch, and I bumped it up almost 300% in the feed rate, and I've just doubled the RPM. Okay, so you can't run it too slow, so make sure you get your speed right before you begin. Okay. What we're going to do now is show what happens to our chip when we feed too slow. We already know what happens to our wallet, it gets thinner, but let's see what happens to the chip. So we're running the same RPM, but we've gone down to a snail's pace of 4 inches per minute. We're still doing that 1/8 depth of cut. Our surface finish will, of course, be much smoother. However, the chips are longer, they're somewhat stringy, and it's taking a lot more time to machine the same area. So that affects your bottom end. You're not making money. In machine shop, there's one saying: we only make money when we are making chips. And you're buying all this capital, you have to make chips in order to stay ahead of the game. All right? Okay, what we're going to demonstrate now is I'm going to use that same carbide face mill, but this time I'm going to be using the periphery and the leading edge to mill out a square corner on this piece. Now it's going to involve a lot more work because the cutting tool will be rubbing against the shoulder we're creating as well as the bottom. Hence there's going to be a little bit of difficulty for the chip to evacuate. So because of that, I've slowed my feed rate down to 12 inches per minute, and I've also slowed my RPM down to 3,000. Okay? There are no set speeds and feeds. You're going to have to alternate those to the work condition with the exact same tool. Okay, so here we're asking more of the cutter, more load and less ability to get those chips out of the way. So let's fire this up and see what happens. You can hear the machine laboring more so than it was previous. And that's okay. We want the machine to work. We want the tools to work. It did it with no trouble. Okay? Now, I'll come back the other side where we can get another look. Okay, here we go. Same parameters. A 1/4 inch cube using the periphery and the leading edge of the cutter with very little room to evacuate those chips. Okay. I apologize for the plexiglass. However, I've got to protect this camera. Let's take a look at the cut we just made a little closer. Remember what I said about the chips are having a little tougher time evacuating? We have to adjust our speed and feed for that. You can see here that we actually have what we call the built-up edge. That's aluminum melting and sticking to our part. Now that's because this chip came free from the one cutter But the next cutter was right in there and squeezed it right into the shoulder. And when you get shear, you get heat, and it will fuse to that. The other side is even more pronounced. Okay? Don't ask me why, but you can clearly see a built-up edge. So it's okay, because this isn't our finish cut, we're just hogging. When we clean that up with our finish cutter, it'll make that nice and smooth. Now, to clean that up, I'm going to go from a carbide to a high-speed steel. And that way, I can ensure I have a sharp corner. Let's say, for example, that this component required a sharp 90 degree. A carbide cutting tool has got a radius right at the very tip. It does that because if it was a sharp point, that would fracture. So the radius gives it a little bit of durability, okay? But with our high-speed steel, we can grind it to a sharp point. So I'll get that tool changed and we'll get right on her. Welcome back. Okay, what I've done now is I've put in an 11/16 end mill high-speed steel 2 flute. Now I've looked at the chart at their recommended optimum cutting speed. In this situation, they're right out to lunch. They're recommending 5,000 RPM, and I can feed it at 22 inches per minute. That might work if I had a stub end mill, constant coolant, and also that I had, in fact, low silicon aluminum. Now I don't know. This is 610, and there's an allowable tolerance for all the materials. Silicon is one of the worst, very abrasive. And if you're doing big heavy cuts and you have a piece of, whether it's steel, aluminum, you'll hear that machine labor if all things are left equal from the last piece. Okay, so what I'm going to do is I'm going to run the machine a little more conservative. I'm going to run it at 1800, okay, and I'm going to utilize a feed rate of 8 inches per minute, so quite a bit less than they recommend. And I'm also going to be using the coolant to intermittently spray by the cutter and the place on the raw material which they meet. Okay, that'll help keep things cool, and also in the case of aluminum, it will help to minimize, not eliminate, but minimize any built-up edge. Now this cutter is pretty sharp, so I'm not too worried about it. Now if it was dull, I'd have as much aluminum sticking to that cutter as I could on the table, okay? So let's see what happens. I'll position the camera where we can get a good look. And we're going to clean up, remember that rough shoulder we hogged out with the end mill? Or rather with the carbide face mill, we hogged out that 1/4 by 1/4. Now we're gonna finish it with our high-speed tool. I'm gonna take 15 thou on the shoulder and 10 thou on the bottom, and we'll examine how it looks. Okay, so we're just starting. And I'm just applying a little coolant, just a squirt now and again. I'm not trying to put out a forest fire, just every now and then. Okay. Okay, so here's this piece now. We can see that the surface finish is nice and smooth. There's no more of that built up edge that was left from the carbide. The corner is a sharp 90 degree, and we no longer have any built up edge. We were using the coolant intermittently. Now, the speed and feed I said that I used was a gentle feed rate. You know, you can go to the chart and see what they're recommending, but the bottom line is it's all going to depend on your setup, your machine, whether you've got a coolant pump or not, and whether your tool is sharp, and the depth of the cut, both on the periphery and the depth along the axis. So that's a guideline. It's up to you to find the proper speed. Remember, we're not a production shop here. We're not making our bread and butter doing this. Whether it takes us 1 minute, 1 hour, 1 day, it doesn't matter. But it certainly matters if you run that cutter too fast and toast it. That's 58 bucks right there, gone in a minute. Okay, so remember, you can always work up to your speed and feed. Now, the range of feed rates would be infinite, wouldn't it? Based on the diameter of your cutting tool, the chip load, the material, infinite. You know, if someone said to me, Ken, I'm going to take all those feed rates away. I'm going to leave you 3. What do you want? I'd say, give me 4 inches per minute. Give me 8 inches per minute. Give me 12 inches per minute. And you know what? I'll be able to do 95% of all the work. So don't make too much out of it. All that I ask is you make sure you've got the cutting speed figured out before you turn that machine on and start going. All right? Okay, there's one thing that I should explain. Whenever we're milling, we can conventional mill or climb mill. Now, what I mean by this is conventional milling would be the same as a boxer. A boxer does this. That's conventional milling. I want to move forward, but yet I'm doing this. Climb milling would be like a swimmer doing the front crawl. I want to go forward. Each time I grab, I help and I pull myself. Okay? There's certain times when you may use either method. One of them is in aluminum. When we conventional mill, the chip, if it doesn't evacuate right away, whether it's because of a shoulder or whether it's just because we're just taking too much off too quickly, if the chip can't evacuate, the next cutting edge plows into it and rubs against the surface as you traverse forward. Okay? Now, when we climb mill, the chip evacuates behind the cutter that removed it, and the next cutter up to bat doesn't strike it. That chip was thrown clear. Okay? So our first cut here, we conventional. The surface finish is fine. Okay? But sometimes you have to change. One thing about climb milling, you need a rigid machine and preferably an anti-backlash. Because, just like the swimmer that pulls, if your table is loose, in other words, backlash, when I engage my cut, it will actually pull the table violently. And that can lead to breaking the cutter outright or premature chip failure. Okay? On a CNC, they have built-in backlash eliminators. You know, you've got your ball screws against your plates. That's very seldom a worry, unless it's old and worn out and sacked. However, on a conventional machine tool, they usually don't have anti-backlash eliminators unless it's a heavy-duty one designed for industry. Okay? These ones obviously don't. But they're still relatively new, they're still relatively tight. So as far as doing light climb milling, you know, test the water first. Try going in with the hand wheel. Make sure it's not going to pull the table. If that works all right, give it a shot with the feed. Okay? So we're going to do the other side, opposite of what we just did now, and we're going to climb mill it. And we're going to look at the surface finish, the difference of surface finish. All right? Okay, same speed and feed. And again, giving it a little squirt of coolant every now and again to help prevent any built-up edge. And you can see the chips are clearly flying clear of the cutter. All right. Okay, I've taken the block out so that we can observe the difference. Now, this surface finish, it's probably hard to see here, if not impossible. This was our first cut where we conventional milled. Now, taking a sharp pencil, here's a tip. This is a poor man's surface gauge. Skilled machinists can tell you a lot about a surface finish using a sharp pencil. So I just run it across and I can feel the radius of the cutter. Okay. It's not bad. Again, we're doing a light cut, a sharp tool, and we were intermittently spraying it with coolant. It's not bad, it's acceptable. But look at the difference when we do a light climb milling. I can see the prism. You know, the prism, the spectrum of colors? That's one tip. When you machine aluminum, you know you've got the right speed and feed when you can see the prism or spectrum of colors. Now, running my pencil, that's as smooth as a baby's bottom. That's beautiful. Okay? So, if you need to make something extremely smooth in aluminum, climb milling can be used to do it. I wouldn't recommend climb milling the entire piece unless, of course, you have a anti-backlash eliminator, but certainly hog it out the way you normally would. Welcome back, milling fans. Let's go through the team's roster. All right. Now, the end mill we're using currently, it is a 2-flute end mill. So we can see that there's 2 distinct teeth or cutting edges. Okay? And it's also a center cutting. So we can see that the leading edge goes from the periphery right to the center. There's a primary and a secondary clearance angle. So it can cut anywhere from here to here, and of course it's mirrored on the other side because it does rotate 360. And we can cut on the periphery. So we can use a cutter like this to cut along the periphery. We can use it to face something, or we can plunge it directly into the material like we would a drill. All right? So that's a 2-flute center cutting end mill, high-speed steel. Very common in the shop, although yours are generally a little duller. This one here is a multi-flute, and it happens to have 6 flutes. We call these flutes, essentially it's a tooth, but they're called flutes because of the helical positioning along the axis. Okay, so it cuts along the periphery just like any end mill will, and it will cut on the leading edge, but only to a certain point. You can see the center is actually concave. So bearing that in mind, yes, I can use this to face mill, but I could not plunge into the work. This area here would not be cutting. It would quickly be pushing. Okay? So multiple flute, but not center cutting. This is a 4-flute rougher, what we call a rougher. And you can see it has serrations along the periphery of the flute. You can see them all there. Now what that does is when you're hogging material, or sometimes you may have a sticky material, this helps to break the chip up into smaller pieces rather than continue on as one long unbroken chip. It's a 4-flute, but again, non-center cutting. Okay. So there's a very large 2-flute, and you can clearly see on this one what I mean by the center cutting. It goes right to the center equally so it can plunge. Okay. Now, what I'll do, swing this thing around. We will demonstrate plunging into that aluminum block with a center cut 2-flute. Okay, here we are. We're all set up. We're going to plunge in approximately 1.25 inches depth. The flute length of this particular cutter is 1.25 inches. What I mean by that is the periphery extends from the leading edge to the shank diameter, the shank diameter being this, 1.25 inches. So I'm going to go the whole thing in depth. Now, this is a lot more work for a cutter because we're plunging in. We're taking the entire cross section of that cutter's diameter and we're plowing it through. So again, like I said, there are no hard one speed, one feed for everything. You have to gauge what you're doing and adjust. So I've slowed the RPM down to about 1200. And I'm going to be feeding by hand, and I'll be able to feel what the cutter is telling me. I'll be able to feel it in my arm through the vibration. And also, as I go in, you'll see me retract the cutter clear to help evacuate the chip. Now, the deeper I go, the more frequently I'm going to have to pull that back out to evacuate that chip, because now it's going to have quite a canal that chip would have to traverse out. a tall order for sure. And I'll also be using a little bit of coolant. Luckily for me, this is going to be a blind hole, so I give it a squirt, and I've got some coolant in there. Okay, so let's see what happens here. Fire it up. I have set my depth stop, so okay. Now here's a continuation of our plunge cutting. This is our 2-flute center cutting end mill. We're all set up. The table is locked in the axis, which aren't moving, which in this case, if I'm plunging, would be my X and Y. And we're using coolant. So here we go. Every now and again, I'm just giving it a little squirt, and I'm plunging right into that part without needing to drill a pilot hole. Again, that is a center cutting 2-flute end mill.